All right, welcome to the Explainer. Today, we're jumping back to the dawn of big data to unpack a system that completely tore up the rulebook on how to store information, the Google file system. So, let's get right into it. The internet was just exploding, right? And this created a data problem on a scale nobody had ever seen before. Google's challenge wasn't just storing all this information, but actually doing something useful with it, using a massive army of regular, everyday computers that were pretty much guaranteed to break. The solution they came up with had to be totally revolutionary. So here's the journey we're about to take. We're going to start with the absolutely massive problem GFS was built to solve. Then we'll get into its brilliant architecture. We'll look at how it actually moves data around. We'll bust a common myth about its design. And finally, we'll trace its incredible legacy right up to today. Now, before they even thought about writing code, the engineers at Google did something pretty wild. They came up with a whole new set of rules for how their system would operate. And these assumptions, well, they flew right in the face of everything people thought they knew about building reliable systems. This right here, this is the GFS philosophy. And that first point is the big one. Instead of spending a fortune on fancy hardware that might not fail, they just assumed that cheap computers would fail, constantly. So they built the fix right into the software. That idea, plus designing for gigantic files and massive continuous data streams, that was the mindset that literally changed everything. So how on earth did they actually build it? Well, this is the GFS architecture. It's a design so important that it's practically a standard question on computer science exams. You really have to get this blueprint to understand how big data actually works. And this diagram shows you the beautiful simplicity of the whole thing. You've got three main players, a single master, a whole bunch of chunk servers, and, of course, the clients. Those are the apps that need the data. The absolute genius here is how it separates the brains of the operation from the brawn. So you can think of the master as the system's librarian. It knows everything about where the data is, all the file names, the structure, the locations, but it never ever touches the actual data itself. It's just the coordinator. The chunk servers, well, those are the bookshelves in our library. These are the absolute workhorses of the system. They store all the data on their own hard drives, and they do all the heavy lifting of sending that data to the clients whenever they ask for it. And we're talking hundreds, sometimes thousands of these in a single system. And what about the books on those shelves? They're called chunks. Files get chopped up into these big 64 megabyte pieces. And that large size is a super important design choice. It means if your app needs to read a huge file, it only has to make one quick call to the master to get the locations of a whole bunch of chunks. This keeps the master from getting bogged down and makes the whole system run incredibly fast. Okay, so now that we have the architecture down, how does an application actually get data in and out? This is where we see the whole system come alive. When you read a file, it's all about efficiency. The client first just asks the master, hey, where can I find this piece of data? The master gives it the addresses. And here's the crucial part. After that one little interaction, the master is completely out of the picture. The client goes straight to the chunk server to get the data, which prevents this massive traffic jam at the one central master node. And this picture shows that direct line of communication perfectly. See that big, thick arrow? That's the actual data flow. It goes straight from the chunk server to the client. The master isn't involved in that heavy lifting at all. Now, writing data is a bit more complicated, and for a really good reason. GFS keeps multiple copies of everything, just in case a server fails. So to make sure every copy stays perfectly in sync, it uses this really clever coordinated dance. The client sends the data to all the copies, then tells one of them, the primary, to take charge. The primary decides the exact order for the changes, and then tells all the other copies to do it in that same exact order. It's how you guarantee consistency. This diagram really shows off the genius of the write process. It separates the flow of data from the flow of commands. You see, the data, the thick arrows, is streamed efficiently to all the replicas at once, but the control commands, the thin arrows, they follow a very strict path, all managed by that primary to make sure everything happens in the right order. Okay, this brings us to another classic question you might be asking yourself right now. If you have thousands of computers all talking to one single master, wouldn't that create a massive system-crashing bottleneck? And the answer is just so simple and so brilliant. It's all right here. The master only deals with metadata, the small stuff. It never, ever, ever touches the actual file data. Clients cache that metadata, the chunks are huge, so the master's workload stays incredibly light. All the heavy lifting, all those terabytes of data flying around, that's handled directly between the chunk servers and the clients, no bottleneck. Now, a set of ideas this powerful, embracing failure, scaling out on cheap computers, separating your concerns, it wasn't going to stay locked up inside Google. It actually inspired a whole new movement in how we store data. This led directly to the rise of NoSQL databases. The name stands for Not Only SQL, and they were built from the ground up to handle the new realities of big data. We're talking massive volume of data and a huge variety of data that just didn't fit nicely into the neat little tables of old-school databases. And this new world just exploded with different options. You've got document databases like MongoDB, super fast key-value stores like Redis, column family stores like Cassandra, which was directly inspired by Google's next big thing, and even graph databases like Neo4j, each one optimized for different kinds of huge-scale jobs. But underneath all of these systems is this fundamental law. You could almost call it a law of physics for distributed computing. It's called the CAP theorem, and it says you have to make a tough choice. You can have consistency, meaning everyone sees the exact same data. You can have availability, meaning your system always responds. And you can have partition tolerance, so it works even when the network gets messy. The theorem proves you can only ever pick 2 out of 3. Every single designer has to choose what matters most.
So after this whole deep dive, what are the big takeaways? What are the core lessons from JFS that are still shaping our world right now?
It really all comes down to this core philosophy. Embrace failure. Don't fight it, build for it. Optimize for your specific, massive workload. Separate the brains from the brawn. And finally, build your apps in your storage system together so they work in harmony. I mean, these aren't just the keys to understanding GFS. They're the bedrock of pretty much all modern big data systems today. And that leaves us with one final fascinating question. Now that we're in the age of AI, with data growing at a speed that makes the early 2000s look tiny, are these foundational lessons from GFS still the right blueprint? Or is the next explosion in data going to demand a whole new, equally radical revolution in how we think? That's the challenge that engineers are tackling right now.